everybody, welcome back to Markov Processes. When we last left off, we were talking about putting a longer history into a Markov framework. We were looking at a particular example where we had items coming off an assembly line with some production process, and the item would come off and be labeled as either good or defective. Now, the chance of it being defective really had to do with the quality of the raw materials going into the assembly line, and the quality of raw materials going in would actually cause us to have maybe multiple defectives in a row because there was an issue with the particular batch of raw materials going in. So we had all these rules that if you have, for example, a defective item coming off the assembly line, the next item is more likely to be defective. But even more than that, we had a specific dependence on the quality of an item and the previous two items, which is not very Markov because the quality of an item should depend only on the quality of one previous item. So we had some rules like if the last two items were good, the next will be defective with probability 0.05, and a bunch of other rules that I'm not going to repeat for you. We've already been through this, but ultimately what we did was we redefined a state space where we paired items together, or we paired the quality together. And we're talking about a state space where we have good and good, or good and defective, or defective and good, or defective and defective. And I'll remind you of what these positions represent in a moment, but we did work out a transition probability matrix, and we got something that looked like this. So let me get right to the questions, and while we answer these, I'll remind you of what it means to have a good good and a good defective. Actually, let me say something about that right now. If you see good good, that means that either your current item was good and the previous was good, or the previous was good and the one before that was good. It just represents two goods in a row. Whereas if you see something like good defective, like up here, it represents an item being good followed by an item being defective, or maybe your current defective and the previous good. The time homogeneity, it doesn't matter what I call previous or current as long as we're consistent. So this good good to good defective, we really have an overlapping space. This represents us seeing a good and then a defective. We go from good and good to good and defective, and there's always an overlap position in between, which is why you see a lot of zeros in this transition matrix. And that would be, for example, if I go from good good to defective good in one step, that can happen because it would be good, and then you would need defective and then good. That overlapping piece, we just don't have it. And that's where we have zero probabilities. So let me remind you of the matrix and keep that in the corner down here and ask you some questions. Given that the current item is defective, but the previous one was good, what is the probability that the next one is good? So there's nothing fancy going on here. We're not skipping any time steps. This, in fact, can be read directly out of the matrix. Let me make three positions in time here and maybe call this center position the current item, and then we have previous and next. And so the current item is defective, so that's a D. And we had that the previous one was good and the next one is good. So we're looking at a sequence of things coming off the assembly line like this, but it really corresponds to us moving from good followed by defective to defective followed by good. And we can go straight into the transition matrix and read this, and it is right here. The answer is 0.3. So that one was just a warm-up to make sure we know how to read the transition matrix that we built last time. So I have another question for you. If the current item is defective, but the previous one was good, I now want to know the probability that the next two are good. So let me try to draw some positions corresponding to maybe a current item right here. I need to leave a space for a previous item over here, and then have the next two be good. So if you pair these up, we've got good defective to defective good to good good. This is two moves from the transition matrix. So I'm going to start over here at good defective, and we have the independent increments property of a Markov chain that says that we just need to multiply the transition probability. So I'm going to go good defective to defective good and grab the probability of 0.3 right here. And then I'm going to go defective good to good good and grab the 0.9 probability right here. And we get an answer of 0.27. Again, I am multiplying here, and I'm not saying that each state is independent of the previous state. It's definitely not. But the transitions are independent. The fact that I transition from this state to this state has nothing to do with where I'm going to go next. Where I'm going to go next to this point right here only depends on where I am here and not where I came from or how I moved between these two states. So the states are not independent, but the transitions are independent. Now, before I move on, I just want to say that you might think that this is us going from good defective to good good in 2 time steps. And so maybe you should square the matrix and grab the single entry that goes from good defective to good good. This is not the right way to think about it. It actually will work here. I'll tell you why in a moment. I am not doing a 2-step transition here where I'm skipping something because I do care about specifically where we are in between. So I'm not saying what is the probability of going from good defective to good good in 2 time steps. I'm asking about a specific set of transitions. I'm not skipping any time steps. At the same time, for this kind of overlap example, there does happen to be only one way to go from here to here in 2 time steps. So if you did square this matrix and grab the entry that takes you from good defective to good good, you will get the right answer. But it's not the right way to think about this problem because we're not skipping time steps. So I would not square this matrix and grab this to this because if you do that, you are not taking into account where you need to be in the middle. It's just that in this example, there's only one place you could be in the middle, so it happens to work. One more question. This is not something you really want to be doing a lot of, this smashing the longer history into the Markov framework. I only have 2 states here, and I only have 2 time steps of dependence, and you can see that this is going to get really bad really fast. I just wanted sort of a proof of concept here that we could do this sort of thing. So for my third question, given that the current item is defective, but the previous one was good, I want to know the probability of seeing at least one defective item in the next 3 items. So I'm going to draw out some positions here, starting with a good and defective. This is my previous and current day. And then what goes here? So in here, I can put any sequence of G's and D's as long as I have at least one D. So I could have all 3 of these be D. I could have 2 G's and a D in any order. There's lots of things to consider, but I'm going to think of this event that consists of a lot of possibilities. And by the way, we can write out every possible outcome here that satisfies what this question is asking, but then we would have to add them all together and you would get the right answer. However, there's an easier way to do this. We can just look at having all goods here because this event is the complement of what we really care about, where I have at least one defective here. So if I compute this probability and subtract it from 1, we'll have the right answer. And so what we want is the complement of the event of going from good defective to defective good to good good to good good. So there's actually 3 transitions here. We're going to have 3 probabilities that we're multiplying, and we're going to take this all away from 1. So we get 1 minus 0.3, which is good defective to defective good. You can see that right over here. And defective good to good good is right over here. Good good to good good is right up here. And in the end, we get 0.7435. So that's all I wanted to do for this example, just a proof of concept that we could kind of pile some more history into a Markov framework if we wanted to. So like for an artificial intelligence application, you might think of autocomplete for words. Like if you type a particular word into a search engine and it gives you the most likely next word, that may actually depend on not just the last word, but the previous 2 words or the previous 3 words. There might be a greater and greater probability that it can predict the next word. And so you could do something like this for an autocomplete in maybe a search engine. But on to something new. Recall our weather matrix example. In the last lecture, we had some weather, and the states of weather were either sunny, cloudy, partly cloudy, or precipitation, which included rain or snow. And yes, it's an over-idealized model of weather. And yes, maybe you can't well define what a day is because it might be sunny in the morning, but it's just an example. And we worked out a transition probability matrix. It looked like this. So I'd like you to look closely at this matrix. I'm going to square it, And as you know, if I square this matrix, it becomes a matrix of two-step transition probabilities. So here I've squared it. This notation, this superscript in parentheses, is meant to say this is the transition probability matrix of two-step transitions, but the Chapman-Kolmogorov equations told us that this is equivalent to squaring the matrix, so that's the notation I'm using here, and this is the square of the matrix. So for example, the probability that we go from sunny to cloudy in 2 days is 0.23. I am going to cube the matrix now, and I have a matrix of three-step transition probabilities, which by the Chapman-Kolmogorov equations we know is the same as cubing the matrix, and so the probabilities in here represent the probability of going from one state to another in 3 days, or with 3 transitions. I'm going to take this to the 4th power and make a 4-step transition probability matrix. Look closely at this matrix. Are you seeing anything interesting happening here? I'm going to jump ahead and take like the 10th power of this matrix. And now ask again, are you seeing anything interesting happening here? It appears that all the values in any one given column are settling down to be the same number. Like here, I'm really seeing it. I'm seeing 0.375, and then I get a 1 way out here, but they're getting really close in all cases. For my sunny column, it appears that they're all kind of settling around 0.2306 and change. And if I take higher and higher powers, I think we're going to see these numbers sort of coalescing around a single value for all the rows in any given column, even more strongly, if you will. So what does this number, this 0.2306 approximately, in this first column represent? It represents the probability of transitioning to sunny after several time steps, and it appears to be independent of where we start the chain. So start at sunny, or start at cloudy, or start at partly cloudy, or start in precipitation. But after 10 steps or 20 steps or 30 steps, it appears that the probability you're going to be sunny or cloudy or and so on is going to be the same no matter where we started. In other words, it appears that this chain is approaching some sort of equilibrium in terms of the distribution of states. So if someone were to ask you right now, your best guess based on what you've seen so far, if I run this chain forever, what is the long run probability of seeing the chain in the partly cloudy state? I would say it's 0.375. We're going to formalize this and we're going to take away the approximation and the rounding, but we're seeing some sort of limit here evolving. Consider, if you will, taking the limit as n goes to infinity of the probability of going from I to j in n time steps. I want n to get really large, and I have some questions for you. So number 1 is, when does this limit even exist? Number 2, if it exists, will it be independent of the starting state I? That's kind of what we were seeing in the example with the sunny and cloudy on the previous slide. And is there, if the answer to both of these questions is yes, is there an easier way to find this limit rather than taking powers of a matrix? In fact, can I find this analytically and not worry about matrix multiplication and rounding and anything like that? So this is where we're headed, and it's going to take a little bit, the rest of today's video and most of, if not all, the next video. But keep in mind, we're going to be doing some kind of abstract stuff now, but the ultimate goal is to be able to talk about this limiting distribution for a Markov chain if and when it exists. And I personally also like to call it an equilibrium distribution, because I think of the chain as settling in to each state with a given probability that is independent of the starting state. So I think of the chain as reaching an equilibrium. So now we have a lot of stuff to talk about, a lot of things to define, but we are headed towards finding this limiting distribution if it exists. So the first thing we need to talk about is the idea of classifying states of a Markov chain as having certain properties. So I'm going to jump right in with a definition and say that a state J can be reached from a state I if you can get there in some number of steps with some positive probability. So if, in other words, in symbol actually, if the probability of going from I to j in n steps is positive for some positive integer n. actually for some non-negative integer n, and the fact that n can be 0 is important here. I'll get back to that in a moment. But if this is true, we make an arrow. We write I and then an arrow to j to say that j can be reached from I. It means you can get there, maybe not in one step. Maybe if you look at your transition matrix and you look at the ith row in the jth entry, there might be a 0. You don't have to get there in one step, but is it possible to eventually get there with some positive probability? So this definition, you'll notice that n equals 0 steps is allowed, and we can't actually move anywhere in 0 steps, except we can stay where we are. So a state, starting at state I, we will always be at state I in 0 steps with probability 1, and this is positive, and it's just an artifact of the definition to say that a state I can always be reached from itself, because we are allowing for n equals 0. So again, this is an artifact of the definition. You may imagine a transition matrix where you start at some state I, and you look at the rows, the probabilities of transitioning away from I, and maybe you definitely leave I in the first step, and looking at the rest of the matrix, you can never ever get back. It could be that your probabilities are set up that way, but we still say that I can be reached from itself, even though we're definitely moving away and never coming back, because we are allowing for 0 time steps. And starting at I, you stay at state I in 0 time steps with probability 1. Now, if state j can be reached from state I and state I can be reached from state j, and this does not have to be in the same number of steps, then states I and j are said to communicate, and we write I with a double arrow j like this. The concept of communication is an equivalence relation. And depending on your background, you might already know what this is, and some of you may not. So I'm going to go through it. But an equivalence relation is when you have some sort of binary relationship between two symbols of a set. So my relationship is going to be this double arrow, and it satisfies 3 properties. So the 3 properties to have an equivalence relation is, number 1, the relationship needs to be reflexive. And what reflexive means is that the relationship has to hold between an element of your set and itself. In other words, in the language of communication here, I communicates with itself. This is the reflexive property of a relationship like this double arrow, which could be something weirder. We're kind of defining what it means for states to be equivalent in some way. And this holds by definition because we just said that you can always go from I to I in 0 steps. So you can get there with some positive probability as long as we're allowing for 0 steps, and then you can get back in 0 steps. So this just holds by definition. The second thing in an equivalence relation is that it is symmetric. So what this means is if I communicates with J, then J must communicate with I. And this is totally by definition again, because if I communicates with J, then you can get to J from I, and you can get to I from J, and therefore you can do it the other way around. This is completely trivial based on our definition of communication between states. But this is the symmetric property. So if the binary relationship between these 2 items holds, then it needs to hold when you switch the items, and it totally holds trivially in our case. And finally, to have an equivalence relation, you need a transitive property. And in the context of communication, this just says that if I communicates with J and J communicates with another state K, then I communicates with K. I think this is probably something you believe, but let's prove it. This is the only one that is not completely by definition, and we'll take a few steps to prove, although I have a feeling you believe this already. Let's try to prove it. Now, if I communicates with J, in particular, we can get from I to J. J can be reached from I. So I'm kind of going in one direction here first, and this means that there exists a non-negative integer n such that the probability of going from I to J in n steps is positive. And if we can go from J to K, again, I'm only considering 1/2 of the arrow at this point, this means that there exists a non-negative integer m such that the probability of go from J to K in m steps is strictly positive. Now, I claim that we now have that the probability of going from I to K in n plus m steps is greater than or equal to the product of these 2 probabilities. I am using the independent increments property of a Markov chain, and we do have a greater than or equal to because there may be other ways to go all the way from state I to state K in n plus m steps, even ways that don't involve the state J at all. So this does not take care of all the ways we could potentially go from I to K in n plus m steps. And if this is enough for you, then I think it's okay to look at this and say by the independent increments property, I know that one way to go from I to K to n, but I think this is a fine statement. But I would like to look at this in a little more detail using the Chapman-Kolmogorov equations. The probability of going from I to K in n plus m steps is supposed to be a sum over, so I want to run over all states in the state space, and I want to save state K. Well, I have state I and state K and state J accounted for in this computation. So I'm going to use like an L. This is my kind of L. And I'm going to sum over all states L in the state space S, the probability of going from I to L in n steps, times the probability of going from L to K in m steps. And L runs over everything in the state space. And as it does that, it's going to hit the state J. So this is going to be greater than or equal to the probability of going from I to J in n steps times the probability of going from J to K in m steps. And L can take on many more things other than state J, but this is one of the terms in this sum. And so, therefore, this sum is greater than or equal to one of its terms, right? It might be equal if all the other probabilities are 0, but it's greater than or equal to one of the terms, and both of these are strictly positive, so the product is strictly positive. And so what we have is we've exhibited a non-negative integer, which is n plus m, for which the probability of going from I to K in that number of steps is strictly positive, and we know now that K can be reached from I. Ultimately, we want to show that I can be reached from K, but the process is exactly the same. So you need to show that side or just claim it's the same like I just did, and then you're done. But if you do want to write out the other direction, do not reuse the time steps n and m, because those were chosen specifically because we knew that we could get from I to J in n steps, and I don't know that I can get from J to I in n steps. So you should really use different numbers of time steps when you go the other direction, because maybe I can find an integer such that I can get from I to J in 3 steps with positive probability, but to go the other way, it might take me 5 steps. So I wouldn't use the same n in that case when I'm trying to write this in the other order, but essentially we've proven it. So we have proven the transitive property, and we have that communication is an equivalence relation. Again, that just means it satisfies those 3 properties: the reflexive, the symmetric, and the transitive properties. And because of this, when you have an equivalence relation, which is some sort of binary relationship, you take a set and you take 2 elements of the set and put some symbol between them and make sure it satisfies those 3 properties, then it allows you to divide the elements of the set into classes of equivalent elements. And they're known as equivalence classes. But for us, we'll actually specifically call them communication classes. So states that communicate go in the same class. States, if you can get from one state to another state and back again, you group them together into a class. Okay, so these 2 pictures represent collections of states. And within each blob, I've got all my states that communicate, and the next blob has a whole bunch of different states that communicate. And because of the separateness of the blobs, I'm saying that states in here do not communicate with states in here. That does not mean I can't move from a state in here to a state in here. But if I can, we will never be able to move back, because if so, then this should have been one big blob. So starting from state I, if I could somehow get to state L, then, and maybe I can move between other states in here that I haven't even plotted, I should not be able to move back to J or K or I. Otherwise, I would get from L to I would have gotten from I to L. They would have communicated. They should have been in the same class. So I think if this doesn't make sense, let's look at an example. I'm just going to make up a Markov chain with states 1, 2, 3, 4, 5, and here is a transition matrix. And what I'd like us to do is to find all of these so-called communication classes. So I'm going to start with state 1. You can see that I can go from state 1 to any other state in the entire state space. That doesn't mean I can come back, So we don't yet have communication. But if you look at the one column, you can see that I can go from state 4 to state 1. So you can see I can go from 1 to 4 and I can go from 4 to 1 in just one time step. That's enough to say that they communicate and they should be in the same communication class. So I'm going to add state 4 to this particular set. I'm writing my different classes as sets of elements. And let's see if there's something else we can get in here. So from the 1 column, you can see that I can't go back to 1 from any other state directly, but that doesn't mean, if I can go maybe from 1 to 5 and then from 5 to 4, then I could get back to 1. And then I could say that 1 and 5 communicate. Again, it's not a one-step thing. One that's really sticking out like a sore thumb here is state 3. It is an absorbing state. I can't go from state 3 to anywhere else. State 3 only communicates with itself and it gets its own class. So I'm going to put it in its own set. And then if you zero in on states 2 and 5, you'll see that from 2, I can go to 2 or 5. And from 5, I can go to 2 or 5. So 2 and 5 clearly communicate and can't get anywhere else. So they are in a closed set of states, if you will. I'm going to call this 2 and 5. And then we basically have proven that states 1 and 4 aren't communicating with anywhere and with anything else, because if you go from 1 to 3, you're stuck at 3, you never get back to 1. So 1 and 3 do not communicate. And if you start at 4, you maybe go to 1 and then to 3, but you can't get back, you'll get stuck. So let me finish out the set 1 and 4. The set 1 and 4 is one of those examples, like I tried to draw with blobs on the previous slide, of a class of states that you can leave, because starting from 1, I can move, say, to state 5, but then I'll be stuck between 2 and 5 and I'll stay in this class forever and I can't get back. If I could get back, then the classes 1 and 4 and 2 and 5, they should have been combined in the first place. Let's look at this sort of thing a little more closely. So starting from state 1, it's possible we never return to state 1. We could pop out to state 3 and be stuck there. We could pop out to 2 or 5 and be stuck in that class. And we say that state 1 is a transient state. This is a state where you have some positive probability of escaping, never to return again. Starting from state 1, you could stay at 1, stay at 1, stay at 1, go to 4, come back to 1, go to 4, come back to 1, stay at 1. You may return several times, but if there's a positive probability of escaping, never to return again, then we say that the state is transient. And state 4 is also transient for the same reason. You see that we can go from 4 to 1, and then from 1 to maybe 3 or 2 and 5, and we'll never get back to 4. I will formalize transience with actual things you can prove and not just have to argue like this. But for now, I hope the idea kind of makes sense that state 4 is something where you have a positive probability starting at 4 that you can never return again. I have a definition for you. We just kind of defined transience in the middle of an example, but a state I is said to be recurrent if starting from state I, the chain will return with probability 1. And this is actually not always said, but this is what is meant here is that it will return in finite time with probability 1, although there's no upper bound on the time. So it may take a really, really, really long time. In the next video, we're going to break down the idea of a state being recurrent to ones that are going to be sort of more quickly recurrent than others. States where you can actually wander away for a while, but will return. So it's just a definition right now. A state is recurrent if you will return with probability 1. And that implies infinite time, because if it takes an infinite amount of time, then you're never really returning. The definition of transience is usually given as not recurrent. It's one or the other, although I like I think it's a little more concrete in my brain to say that a state is transient if you can find a way to escape, never to return again with some positive probability. So going back to our example, states 1 and 4, I claim are transient just by conversational argument. We are going to do this more formally. And there is some positive probability of escaping these states, never to return again. We're going to prove that transience and recurrence is a so-called class property. What this means is if you have a class of states, a communication class, where everything in that class communicates with everything else, then if just one of those states is transient, they all must be transient. And I think you get the idea because we've argued that state 1 is transient. You can go from state 1 to state 3, never to return again. You can't go from 4 to 3, but starting at 4, you can go to 1, and then you can go to 3, never to return again. And so you can almost think of state 4 as getting that transience from the very fact that it communicates with state 1. We're going to prove that if one state communicates with another, you have the double arrow, you can go in both directions, then they're either both transient or both recurrent. So we say that state 1 and state 4 are transient states, and the entire class we call a transient class. State 3, which happens to be an absorbing state in this example, is a recurrent state. You will return with probability 1, and this is a really strong form of recurrence, if you will, because you are stuck there and not going anywhere. So you're definitely returning with probability 1. And we are going to see that recurrence is a class property. So in my class here that has 3 in it, there's only 1 element. But if there were more states in this class, if any one of them is recurrent, the rest are recurrent as well. And an entire class, just like we said for transients, an entire class of communicating states is either recurrent or transient based on what each of the states are. And I just claimed that all of the states have to have the same they could either be labeled transient or all be labeled recurrent, and in which case you would call the entire class either transient or recurrent. So just to finish this off, states 2 and 5 are recurrent. Actually, I would like to prove this to you. So recurrence is that if you start at one of these states, you will return in finite time with probability 1. And sometimes at this point, people ask, well, isn't there a chance you maybe go from 2 to 5, and then you go 5 to 5, 5 to 5, 5 to 5, and you just sort of get stuck there spinning around and going from 5 to 5? How do I know I have to come back to 2? In other words, how do I know that state 2 was actually recurrent? So I want to prove this for this particular example. And in the next video, we will prove that recurrence is a class property. But I just want to get rid of the mess here. And let's just say I have a 2-state Markov chain, and I want to make the transition probabilities a little more extreme. If you like, make them even more extreme. So make the probability of going from 2 to 2 0.00000001, and the probability of going from 2 to 5 0.99999. I've lost count, but you know what I mean? Make these really extreme. So starting from 2, it looks like you have a high probability of going to 5. And then from 5, you have a high probability of staying at 5. Make these as extreme as you want, but I want to prove that starting at state 2, I will definitely return in finite time. To do this, I am not going to use these specific numbers. I'll use more general transition probabilities, little p sub 2,2, p sub 2,5, p sub 5,2, and p sub 5,5. And I'm going to assume all of these are positive so that we can move around the space, even though the probabilities may end up to be pretty extreme. I want to assume they're at least all positive. At the same time, this implies that they're all less than 1 because, for example, these 2 probabilities have to add up to 1 because they correspond to the 2 row of the transition matrix where these 2 have to add up to 1. So if any one of them was 1, then there'd be another probability that would be forced to be 0. So by assuming they're all strictly positive, we're actually also assuming they're all strictly less than 1. And again, make these probabilities really extreme, but I want to show starting at 2, we're going to return with probability 1. So given that x0, the Markov chain starts at 2, what is the probability we return to 2 in finite time? Although I didn't write that here. I can break this up into some disjoint event probabilities that we first return in exactly 1 step, or, so I get to add the disjoint event probability, the probability that we first return in 2 steps, or get to add the disjoint event probability that we first return in 3 steps, and so on. I underline the words first here because it's important. If I just talk about the probability of going from 2 to 2 in 2 time steps, then that does not negate the possibility that we went from 2 to 2 to 2. So we returned in 1 time step and stayed there. So we went from 2 to 2 in 2 time steps, in which case we may not be talking about disjoint events anymore. If I remove the words first all the way down the line here, the fact that we return in 1 step and we return in 2 steps is no longer a disjoint event because 2 steps might be that you went in 1 step and you stayed there, or So it gets a little more complicated. So it's definitely important for when I'm writing that I look at first return times to these states. So the probability we first return in one step, that's just the one-step transition probability that comes out of the matrix. This is little p sub 2, 2. The probability we first return in 2 steps means that we have to move away. So we go from 2 to 5, and then we have to come right back by going from 5 to 2. I get to multiply those two transition probabilities, P25 and P52. The probability we first return in 3 steps means I have to move away, or I would have returned in 1 step, and we'd no longer be talking about the first return in 3 steps. So I have to go from 2 to 5. Then I better not come back because that would be a return in 2 steps. So I have to go from 5 to 5, and then finally from 5 to 2. So I get to multiply these transition probabilities. Whereas if I was first returning in 4 steps, then I'd have to go from 2 to 2. Then I'd have to go from 5 to 5. Then I'd have to go from 5 to 5 again, and then from 5 to 2. And in general, if I first return in n steps, this means that I have to go from 2 to 5. Otherwise, I would have returned in 1 step. And then I have to stay in 5 for n minus 2 time steps. And then I finally have to go from 5 to 2. This is the probability starting at 2 that your very first return is in exactly n time steps. So what we want to do to compute this probability is add all of these up. And so let me just write this out with some notation. This looks like this. The first line I had in the previous slide sort of didn't fit into the pattern, but after that we have all values like this. And I could pull out the P25 and the P52, and I'm left with a geometric sum. This n is actually a power. This should not be n in parentheses, which is an n-step transition probability. We saw that we're just taking powers of P55. Now, P55 was assumed to be less than 1. So we can sum up this nice geometric sum, and we end up with 1 over 1 minus P55. But recall that P55 was 1 minus P52. So this right here is P52, and we get cancellation of this entire fraction with P52. So we're left with P22 plus P25, but that's adding up the elements in the second row of the transition matrix, and those have to add up to 1. So we're done. We have proven that even if we make these probabilities really extreme, starting at 2, maybe you're going to go to 5 almost surely, and then maybe you're almost surely going to be stuck at 5. But as long as there is some positive probability of coming back, you will return with probability 1. And so we have proven that state 2 is recurrent. So now I have some more definitions for you. If all states of a Markov chain communicate, so if you try to break it up into communication classes and you find that you only have one class, we say that the chain is irreducible. Otherwise, we say that the chain is reducible. I want to remind you that our end goal here is to look at whether or not we have limiting probabilities or like an equilibrium distribution for the Markov chain. Remember when I took the 10th power of that transition matrix and we saw the columns trying to settle down? I'm going to have a bunch of theorems for you that say if the chain is irreducible and if it also has these other properties, then the limit exists and is unique and independent of the starting values, and all sorts of nice things happen. We are, again, in a period of building up a bunch of terminology so that we can state and prove some theorems about when the limiting or equilibrium distribution for a Markov chain exists. By the way, note that for an irreducible Markov chain where all states communicate, the entire chain must either be recurrent or the entire chain must be transient. Granted, I have yet to actually formally prove this, but we did state that recurrence and transience are class properties. So if I communicates with J, if I is either recurrent or transient, then J is going to be the same. And if everything communicates, they're all the same. And just like we call an entire class of states recurrent or transient, we would call the entire Markov chain recurrent or transient if it's one big class, if it's an irreducible chain. And so if you bear with me into the next video, I will eventually prove that recurrence and transients are class properties. But right now we have a definition of a chain being irreducible where all states communicate. And then we can say that all states are transient or all are recurrent. So we could call the entire chain itself transient or recurrent. If you have a Markov chain on a finite state space, you must have at least one recurrent state. because transient states are states that if you leave from them, there's a chance to escape, never to return again. If you only have a finite number of states, like our example where we had states 1 through 5, there's no way you can escape everything, never to return again. You have to go somewhere. So the only way you could have your entire chain be transient, number one, you would need one communication class. Everything would need to communicate. But you would need to be able to escape every state, never to return again with some positive probability. And this is actually possible when you have an infinite state space. I'm going to have an example coming up in the next video, or at worst, the one after that. But so like an infinite state space, some sort of random walk. Imagine, let me give you an example right now. Here's an x-axis, and this is time. And then you have integers going up and down, positive and negative integers, and you start at state 0. So maybe you go up with some probability or down with some probability at every step. If you have a, so you can imagine if that your up probability is greater than 1/2, that you could wander off to positive infinity. And so given that you start at any state, there's a chance you will never return again. It's a little bit subtle. We're going to look specifically at such a random walk mathematically eventually, but for now, hopefully it makes sense that if you have only a finite number of states, you can't possibly escape all of them. You need at least one recurrent state. If the chain is irreducible and you can move between all of them and you have one communication class, if you have a finite state space, you have at least one recurrent state, and therefore they must all be recurrent if they all communicate. And we say that we have a recurrent chain. Okay, so just to have a little forward momentum for what we're going to talk about next time when we formalize some of these arguments I made, we're going to be talking about first hitting times and first return times. And I want to define them right now before we go, again, for the purpose of forward momentum. So suppose that Xn is a Markov chain. I want to define a first hitting time on a state I. I'm going to call this capital T sub I. I'm using a capital letter because this is going to be a random variable. And I'm going to define this to be the minimum of all integers n greater than or equal to 0, such that, in math, this colon like this in a set is read as such that xn equals I. This is the first time your Markov chain ever hits the state I. And it could be where you start the chain at time 0, or if you start somewhere else, it will hit at some later time. And I don't know when that's going to be in general when setting up a Markov chain. So this is a random variable known as the first hitting time on the state I. And a very similar random variable is going to be the first return time to state I. I'm going to use a T sub I as well here, which I realize can be very confusing. There's a lot of points in this course and my other courses. If you've taken some of my other courses where I introduce my own notation, my own terminology, I say, well, I'm going to call this, but you're never going to hear that anywhere else. But at some places, I do like to hold the line with consistent notation and not be too crazy and inconsistent with everyone else. And it is really common for people to use the same letters here. So T sub I is the first return time to state I if the minimum integer at times n greater than or equal to 1. So I'm no longer allowing n equals 0 in here. The first time the chain is going to be in state I at times greater than or equal to 1. But this only makes sense as the first return time to state I in the context where x0 was I. So you have to start at I, and if you're talking about a first hitting time on state I and you started at I, your first hitting time is 0. But for a first return time, you do want to allow a movement away. So you only want to look at times 1, 2, 3, not at time 0. So I think that's good enough to go for next time. We're going to use hitting time and return times to more formally write down the definitions of recurrence and transience. We're going to prove that recurrence and transience are class properties that we've argued that a few times here today, but we're going to prove that really formally. And we're going to break down recurrence of a state into faster and slower types of recurrence. So to take you for a moment back to the random walk on the integers, if you start at state 0 and maybe you go up or down at each time step, and say you go up with probability 1/2 and down with probability 1/2. If that probability is balanced, I claim that you're not going to float off to positive infinity or negative infinity. However, if you get a few ups in a row, and maybe you make it up to state 8, then you still are going up and down with equal probability. So it's going to be hard to get back down to 0. You're going to tend to sort of stay there. And so if you talk about this random walk with the up and down probabilities being equal, we're going to see that state 0 and all the other states are recurrent, but you can wander away and it may take you actually the expected number of steps to return. We're going to see that the probability you will return in finite time is 1, but the expected number of steps it's going to take is infinite, which is a little crazy right now. And that's going to be a really slow form of recurrence, as opposed to when the expected number of steps to return is finite. So we're going to break down recurrence a little bit further. I hope to see you in the next one.